Hello student, to the lecture number 3 for the course is Physics of Linear and Nonlinear Optical Waveguides. Today we will going to cover the Poynting vector and Maxwell's equation in dielectric medium that we have started in the last class. So, this is a continuation of the previous class. Also, I like to in this class I like to mention about the textbook and reference reading. As a textbook for this particular course, we have two books. So, Optical Waveguide Theory by Snyder and Loeb. This is one book you can read as a textbook, and another book, Introduction to Fiber Optics by A. Ghatak and K. Tyagarajan, very popular book in India. So, you can also have a look to this book as a textbook. For reference reading, Fundamental of Optical Waveguide by Okamoto is a good book. You can check that book, and also the book by G.P. Agarwal, Introduction to Nonlinear Fiber Optics. It is a very important book in the field of nonlinear fiber optics or nonlinear waveguide. So, when we cover the nonlinear part, nonlinear characteristics of the waveguide, then this book will be important and you can go with this book. And finally, Optical Electronics by A. Arif, it is also a very well known book. So, these are the textbooks and reference reading. Today we have lecture number 3, and in lecture number 3 we start with the Poynting vector. So, we start with Poynting vector. So, by definition, Poynting vector is defined in this way: S is equal to E cross H or 1 by mu naught. If I deal with free medium, E cross B, vector B. So, S, which is our Poynting vector, is the energy flow per unit area per unit time. So, eventually this is power divided by area, which is intensity. So, eventually it tells us about the intensity of the system and also the power flow, and this is the recipe E cross H through which you can calculate the Poynting vector, and we will try to find out what is the value. And in order to find the value, we directly use the relationship between B and E, which we derived last day. So, we have the frequency omega multiplied by B is equal to propagation vector k cross E. So, I will going to use this equation to and put it here to find out what is the expression of S in terms of electric field E. So, S then will be 1 by mu 0 vector E cross, and in place of B I will put k cross E 1 divided by frequency omega. So, it is eventually S is equal to 1 divided by omega mu 0 vector E cross k cross E. It is like A cross B cross C, and we are going to use this vector identity to resolve this, and we know what is the vector identity for A cross B cross C. It is BCA CAB. This is the formula we normally use, and if I have BCA, so it should be K E dot E minus vector E K dot E. Vector E K dot E. So, this value K dot E we know is 0 in free medium, because we have grad dot E is equal to 0. So, equivalently I can write I in place of grad operator, I can replace I if it is a plane wave solution. Last day we derived that. So, this term is 0. So, I have simply K divided by omega mu 0, then E square and K unit vector. That should be the value of my Poynting vector S. S should be K omega mu 0 E square and the unit vector K. That means the Poynting vector is along the direction of the K. Now, I can simplify this, because omega is equal to Ck, that we know, this is the relation. So, from that, and also 1 by mu 0 epsilon 0 is C square. So, I use these two equations to find out the value of the A in a more compact form, value of the S in a more compact form, Poynting vector S in more compact form. So, it should be simply 1 divided by mu 0 and then K by omega I can write at C, K by omega I write 1 by C and then E square and K unit vector, and again mu can be replaced by C square, so epsilon 0. So, epsilon 0 C 1 C will cancel out and we have E square K unit vector. So, this is the term I have. This is basically the relationship with the S vector with the amplitude of the electric field E. Now, we know that the electric field, if the electric field is sinusoidal in nature, I can write is a plane wave solution form as this, cos of K dot R minus omega t. This is the solution of E we know, this is the plane wave solution we know. And now, if I want to find out the average value, because this is changing with respect to time. So, if I want to find out the average value, so what is E square? So, E square is E dot E. So, I have E 0 square cos A square K dot R minus omega t. This is the value of E square. Now, if I want to find out the average value of the S, average magnitude of the S, so I need to do the averaging on the right hand side as well. So, it should be epsilon 0 C the average over E square, and E square we know it is changing in this way, E square cos square k dot r minus omega t. If I do the average of cos square k dot r minus omega t, I simply have a half term, because we know the average value of cos square term is half. So, eventually I have this quantity, which is my intensity. So, in this straightforward calculation, we find the relationship between the Poynting vector with the intensity. Poynting vector, average value of the Poynting vector is essentially the intensity. So, this is a very important expression, because this gives us the idea how the intensity is related to the peak value of the electric field E 0. Well, now the next in the next part, we will going to calculate, we will going to find out Maxwell's equation in a dielectric medium. So, we are going to find out what is the Maxwell's equation in dielectric medium, and then from that we are going to derive the Maxwell's wave equation. So, if I write one by one, so in the dielectric medium the Maxwell's equation will have this form: grad dot d is equal to rho f. Rho f is the free volume charge density. Grad dot b is equal to 0. Curl cross E is minus del B del T. It is not going to change inside the medium. In the medium, something, if something is changed, that is the equation 1 and 4, which is containing the source terms. And finally, curl cross H is equal to Jf plus del D del T. Now, we should remember that the vector D is epsilon E, and if the system is not non-magnetic, B is mu 0 H for non-magnetic systems. Now, we will going to make use of this 4 equation to find out the wave equation, how an optical wave is propagating inside a dielectric system. And in order to do that, first we consider that rho f and j f, these things are 0. So, there is no free charge density and no free current density. So, the free charge density and free current density are not there. In such case, in this equation 1 and 4 is modified. However, equation 2 and 3 will not going to modify. So, equation 1 will be simply grad dot D is equal to 0, and equation 4 will be curl cross H is equal to minus of this quantity. Okay. So, equation 3 also can be written in terms of D and H. because it will be useful in our calculation. Equation 3 I can write it as this. I just replace the value of E and B in terms of, I replace the value of E and B here, the value of E and value of B I just change in terms of value of D and value of H. Well, one thing you should note here when you do that epsilon is not a function of space, then only you can take this epsilon out of the curl operator. So, the system is isotropic and homogeneous at the same point. Well, now what I do, I make a curl of equation 3. If I do that, then it should be 1 by epsilon curl of D. This quantity in the left hand side is curl cross D, in the right hand side it should be del T, then curl cross H. Now, curl cross H from equation 4 I have this one. So, I am going to use this equation here, and if I do, I can have in the left hand side 1 by epsilon curl cross D. Again, this is a well known vector identity and it should be minus of Laplacian operator D plus gradient of D, this, and in the right hand side it should be minus of mu 0 del T square because curl cross H is minus of del T. So, I should have from equation, so I should have this curl cross, so it is D. So, now so here this equation is plus, so I make a mistake here. So, this equation is plus because it is J plus these things. So, then this minus sign is there. So, finally, I can see that this term will be 0 because from equation 1 we have dot D is equal to 0 because the rho f is 0, the free charge density is 0. So, then we eventually have square D is equal to mu 0 epsilon to D del T square. Well, now if I want to write this entire equation in terms of electric field E, then I need to replace again because D is epsilon E. So, I can replace this thing here to make the entire equation in terms of, to write this entire equation in terms of E. So, I can have that grad square E is equal to mu 0 epsilon del E del T square. Now, epsilon, which is a susceptibility, can be written as epsilon 0 multiplied by epsilon r, the relative susceptibility, and this epsilon r is we know that root over of epsilon r is basically the refractive index of the system. So, epsilon r is equal to n square. So, we have epsilon 0 n square. We can put this equation here in the wave equation. So, the wave equation finally comes out to be the wave equation inside the dielectric system, dielectric medium, will be grad square E equal to epsilon 0 mu 0, because mu 0 is already there and I replace the epsilon 0 as epsilon 0 multiplied by n square d2 E, the vector sign, dt square. And again mu 0 epsilon 0 is equal to 1 divided by c square. So, eventually I have an equation that we are going to use later. C square is d2E dt square. So, this is the wave equation for a dielectric medium, the system when the electromagnetic wave is propagating inside a dielectric medium. So, this is the equation one can expect, one can have, and you can see that n is now associated with this equation. So, refractive index is going to play an important role, and obviously in the free system, in the free medium, n is 1. So, this equation will be simply grad square E is equal to 1 by c square d2E dt square, but here since the refractive index are there, because the medium will going to give some kind of resistance to the propagating wave in terms of refractive index. So, this refractive index, the information of the refractive index should be here in the equation. Well, after that we will now try to understand few thing, which is Snell's law, and the concept of total internal refraction. Total internal reflection, or in short TIR. So, we all know the Snell's law, nothing special. So, this is, suppose we have two medium, one is N2, another is N1, such that N1 is greater than N2. So, in such medium, if a light is coming in this way, so it is refracted in this way. So, I have angle here theta 1 and I have angle theta 2. So, now Snell's law says that N1 sin theta 1 is equal to into sin theta 2. This is simply the Snell's law. And sin theta 2, it is for our, I can write this sin theta 2 in this form, n1 divided by n2 into sin theta 1. Why I am writing sin theta 2 in this form? Because I am going to use this form in our next class when we try to understand something called evanescent wave. Before concluding today's class, let us quickly understand what is the meaning of total internal reflection. So, the total internal reflection, if I have, so let us consider three conditions. I have n2 n1 and n1 is greater than n2. So, this is simply when the light ray is falling here. So, I have angle theta 1 and angle theta 2, and it is following the Snell's law, like n1 sin theta 1 is equal to n2 sin theta 2. In this case, if I now increase the angle of theta 1, so obviously this angle theta 2 will going to change, and at some point this angle will be 90 degree. So, this angle is a spatial angle, theta 1 is a spatial angle, theta c, this is called the critical angle. At critical angle, what happened, that this ray will be like here and this angle will be pi by 2. So, we have a spatial equation, and this equation is n1 sin theta c is equal to n2, or sin theta c will be n2 divided by n1. And now if I launch the light more than the angle of the critical angle, suppose this, then this ray will be reflected back, and this is the phenomena called total internal refraction. So, this is the angle and this is my original angle theta c. So, this is my theta c, and I launch the light with an incident angle theta 1 that is greater than theta c, and this angle will be now theta 1 as well, because it behaves like a reflection. So, here also in principle, since it is coming through the boundary condition, this equation, this Snell's law is coming through the boundary condition. In principle, the equation n1 sin theta 1 equal to n2 sin theta 2 should valid, and if it is valid, then we will going to see in the next class that the angle theta 1 will be giving us a imaginary value. So, from the imaginary value we will try to find out what will be the fate of this wave. So, some wave will pass through this boundary, and which we call the evanescent wave. This evanescent wave eventually die out. So, that part we will going to see in our next class. So, with this note I would like to conclude. So, today we mainly cover the concept of Poynting vector, then try to understand the wave equation in a dielectric medium, and then very briefly we understand what is the meaning of Snell's law and total internal reflection. So, in the next class we start with total internal reflection and try to find out more on what is going on there when the incident angle is greater than the critical angle. Thank you for your attention.